Hi all, my name is Fawad Najam and I am an assistant professor of structural engineering at NUS Institute of Civil Engineering. This video is the first of the series of videos which I will be uploading for explaining some of the basic concepts in modern structural engineering. In this first video I will be discussing about an approach called performance-based approach for the seismic design of buildings and structures. I'll start with first explaining what the process of structural design is. It's a process of proportioning our structural elements or components of a structure which will ensure a safe resistance of applied actions. These applied actions can be load effects, can be the requirements from architectures or architectural staff, or some other constraints which we can face in a real structural engineering project. The process itself is a systematic investigation, finding structural behavior and forcing the structure to kind of obeying a desirable performance in the design life of a structure. The output of this process is the minimum material requirements, material specifications, cross-sectional details, reinforcing details, and the overall configuration of different structural element and the overall structure also. In this process we basically calculate all the applied seismic demands if the applied loading is the seismic loading, and we have to provide the enough capacity against each of the demand to resist that applied effect or the load action. The overall concern, the prime concern in this whole process is the structural safety. Now in this process different building codes guide us during the process. There are different families of building codes which some of them provide us the amount of minimum loading which we should be applying to our structures in their design life, or some of them guide us in the detailing and the analysis procedures which should be used to analyze these buildings for the structural design purpose. Now our building industry primarily relies on these building codes and standards. These codes basically specify different requirements and provide different solutions for those requirements. They also prescribe various simplified analysis procedures, and the underlying assumption is that if you follow those all requirements and the clauses, set of rules, you will be safe. So in a sense building codes basically implicitly ensures the building safety or the public safety at large. These building codes basically, instead of explicitly approaching to the problem of structural design or behavior, they implicitly ensures building safety through different safety clauses or provisions or different checks and empirical expressions. These codes are primarily prescriptive in nature. They are cookbook type procedures. They prescribe different you can say step-by-step procedures which a structural engineer is supposed to follow to come up with a supposedly safe design. If you look at the clauses of these building codes, they are all prescriptive in nature. What I mean is that there will be a very specific set of rules, some specific rounded limits with implicit meaning, and the structural engineer is supposed to follow those rules. Just to give you a quick idea about what the structural performance is, I start with an example of the first ever building code, an example of a code called Hammurabi's code, and that code is around 1700 BC. I mean, Hammurabi was the king of Babylon, and he detailed a building code for the purpose of different kind of construction practices in his empire. One of the example clause which I want to quote here for explaining what the explicit structural performance is, that if a builder builds a house for someone and does not construct it properly, and the house which he built falls and kills its owner, then that builder shall be put to death. This is a classical example of what a performance-based approach towards building codes can be. Without some explicit requirements that the building strength should be this much or should follow these rules, the ultimate performance is what is required. The collapse performance is explicitly defined in this clause, and the consequence of non-performance is also mentioned, without detailed explanation of how you should ensure that the building is properly constructed. This example shows us that the ultimate requirement from the owner point of view is the performance of the building and not the procedure used to get that performance. So if that performance is the basis of structural design, if that performance is guiding your design, then the approach will be performance based approach, and that will be quite different from the prescriptive cookbook type code based approach. Another example I want to give you here is, for example, modern building codes would provide you different safety factors or the minimum dimensions of different structural elements. For example, in case of a parapet, you can find that minimum height can be this much. But why building codes prescribe those minimum heights is to ensure a minimum level of performance which is intended from those components. Instead of using implicit performance objectives, prescribing different numbers or safety factors or some other approaches, empirical approaches, if your ultimate goal is to ensure performance, then the approach will be performance based design approach. Unfortunately, our structural engineers are kind of trained to follow the procedures and equations and rules, and they are trained to be conformists. Instead, the architects, for example, they are trained to dream and to be defiant. I want to give this example that, for example, if I were to ask you to design a water tank, for example, made of reinforced concrete, and I give you some dimensions for that water tank, an ordinary structural engineer should be able to design the reinforcement and the thickness of walls, for example. But if I change that question, if I change it to, for example, design the most cost-effective water tank to hold, for example, 36 meter cube of water, then you don't need to be an ordinary structural engineer to answer this question. You need to be what we call as a structural designer to answer this question. Without giving you some dimensions, some basic requirements, if I tell you directly the function, ultimate output, and you are supposed to do that to come up with a structure to fulfill that function, that is a difference between structural designer and a structural engineer. But for example, if I change that question again, and if I ask you to design the most cost effective and beautiful and kind of an amazing water tank which can hold some quantity of water, that in my opinion requires you to be what I call as a structural artist to answer this question, more than an ordinary structural designer. So a prescriptive code based approach will not encourage you to go beyond an ordinary structural engineer. That requires you to go out of the box, to think some innovative kind of solutions, but that you can only do if the ultimate output or the ultimate requirement of structural performance is in your mind. One important question here is that, are all building codes correct? We know that there are different kinds of building codes available, and they differ in their different clauses in terms of safety factors, in terms of load factors, load combinations. So if they all differ, then are all correct at the same time? The answer may be no, because if they all differ, they all can't be correct at the same time. One more question is that, do we inform our structures to follow a particular building code? The answer would be no. For example, one more issue in this regard is that We upgrade our building codes after every 3 to 4 years. So should we also upgrade our structures which are designed according to previous building versions of building codes? That is an interesting question. The structure which is safe according to a previous version of building code may not be safe according to the latest version of building code. And one more thing is that code intend life safety or safety of public at large, but they don't have any limit on the extent of allowable damage or the repair cost or the cost or the time required to repair that building. All of these things, which may be very important, are not covered in these building codes. So there are a lot of issues with the traditional building codes, and a prescriptive approach may not handle some of the real life issues or challenges which we are facing in construction industry today, especially related to structural design against earthquakes. Public wants the answer of a simple question: will our buildings are safe against future earthquakes or windstorms or any other extreme events? The owners of these buildings they are more interested in questions like what level of an earthquake is going to cause some damage in my building, or how much repair cost that building will be undergoing after an earthquake. Will I be able to use that building after a certain level of an earthquake? Or for example, how much time is required to rehabilitate this building after an earthquake? Structural engineers are not in a position to explicitly answer these questions. Maximum they can say is that I have followed the building code, and the building code implicitly ensures that structure will be safe. As long as you follow the building code, you will be protected by the clauses of that code, legally protected by that. This is the maximum you can answer. You cannot explicitly answer all of these questions which owner or public demands from us. To give you an example of how less we know about our structures, I would refer to a very old movie which I once watched. Its name is The Towering Inferno. This movie was released in 1974, and in that movie they featured a high-rise building which was under fire, and what they did when the building was under fire, they called the architect or the structural engineer of that building and asked this question, that how long will this building will take to collapse under this fire? And then they showed that structural engineer he called on all the drawings and all the calculations, everything, and he came up with a number, some few hours. He predicted that in few hours this building is going to collapse, and all of the evacuation should finish before that time. This movie was released in 1974. Today is 2020, and still we cannot answer this question which public was expecting to answer from us in 1974. It's very difficult to simulate the behavior of a building which is under fire, to come up with the answer of this question, that how much time will it take before it collapses. Still we cannot reliably answer this question in 2020, but public was expecting from us in 1974. This tells us how less we know about our complex structural behavior, especially high-rise buildings and long-span bridges. Performance-based approach, on the other hand, it's a new umbrella term for all of the latest technologies which were developing in last 15-20 years in our structural design field. This approach explicitly links the structural performance with the earthquake hazard. Although any loading can be handled with this approach, but this is mostly described or developed for the seismic loading. So this approach explicitly relates the structural performance with the earthquake hazard. It's a tool to know how the structure is going to perform during a certain level of earthquake hazard. So it enables structural engineers to explicitly answer some of the most hard questions which owners or building developers or public at large asks from us, we can explicitly answer them, or at least try to answer in a way which they can understand. In this approach, the structural design criteria is not expressed in terms of some fixed prescribed numbers. That is expressed in terms of minimum performance which we are expecting from that structure. If that performance is okay, that structural design is okay. In this process, that prescriptive clauses of building codes are not required. They can only be used to just come up with the first set of trial design, and then all what is required is that structure fulfills its performance objectives. So what we do is that we use this approach for cases where the traditional building codes are not suitable, and where the explicit verification of the output of structural behavior is required, or some other complex cases where the project is so big that it requires this lengthy or detailed procedure to come up with the detailed structural behavior. In the heart of this process, what it lies is the nonlinear modeling of our structure. So we have to develop a nonlinear computer model which will help us in predicting the structural performance or behavior in terms of extreme earthquake or different levels of seismic hazard. We define these performance levels in terms of like operational, immediate occupancy, life safety or collapse prevention. These are different kind of templates of performances relating to the damage of the structure, which are simply understandable by any building owner or structural engineer or developer or public at large also. So for the very first time in the history of structural design, we are able to communicate meaningfully with the client or with the owner of the building in terms of these performance levels associated with the performance of our structures. We can link these performance levels with the behavior of structures, with all the, for example, damage of the structure, loss of the structure, repair time of the structure, repair cost of the structure. All of these performance levels can be linked to different answers of those questions which the owner asks from us. So all we have to do is to analyze the nonlinear model of our structure under different levels of seismic hazard, so that we can come up with their explicit performance, not some implicit checks on the design which code-based design tells us. We can actually see which beam is being yielded under what level of an earthquake, or which column is being cracked, or which shear wall is being cracked. A nonlinear model have the capability to tell us all of these information after the analysis. In this specific framework, there are two different types of seismic hazard or levels of seismic hazard which we should be using to analyze our building. The first is called the service level evaluation, and then second is called the maximum considered earthquake level evaluation. The requirement, or you can say the expectation from the structure side for both of these levels is different. For service level evaluation, it is expected that structure will not undergo any nonlinearity or cracking or yielding, etc. For maximum considered earthquake level evaluation, we expect that structure can go under significant damage but will not catastrophically fail, will not collapse and result in the loss of lives and other casualties. So the summary is that in this approach, we answer all the questions asked by owner in a manner which he can also understand. And how we are able to do it? Because of the nonlinear structural model, we know the amount of yielding or cracking or any other damage in any structural component for any level of seismic hazard. So we can answer more meaningfully these questions. For example, we can relate the repair cost with the amount of cracking or yielding in the structural elements. We can relate the amount of the time required for repair with all of these things. So whatever damage can be related to the amount of yielding or cracking in structural elements. So and obviously there is a peer reviewer also involved in this process, which checks that the process itself is working right. In this performance based approach, different guidelines and different international standards help us in creating non-linear model and implying and how to assess the structural performance after the analysis. And you should note that these guidelines are not building codes. They don't claim that they should be followed just like a building code. They are just guidelines prepared by international organizations for helping the next generation of structural engineers in applying these performance-based methodologies. In the last, I will also like to mention some of the tools of the trade. Obviously, in order to apply this methodology to real buildings, you must know some of the latest computational technologies, some latest software for structural modeling, and most importantly, you must know some of the latest approaches in nonlinear modeling of structures. That is the core of this methodology. That is the main tool which will help us in converting the structural damage into something meaningful, which we can tell to our owners, to clients, or to the real estate developers, etc. These tools of the trade include some latest technologies, some latest software. For example, you can use ETABS to create a linear elastic model of a structure. In order to create a non-linear model, you can use Perform 3D. Both of these products are from CSI. This is a requirement, a kind of a must requirement. If you want to learn this technology, you must have to learn non-linear modeling in order to apply this technology. I'll see you in some next video about some other concept of structural engineering, or maybe the more extension of this idea, the more explanation of some of the things which I have talked in this video. So till then, see you. Bye bye.